Hi students, welcome to Physics for Everyone classes. This is your Satish. So in this section we can see a very important concept which is AC current is passing through the pure resistor, pure capacitor and the pure inductor. Let us see the first one. Alternating current is passing through the pure resistor. There we have got the circuit. And here we are using the AC source. You can see the symbolic representation. The sine wave is there in the circle. It indicates the AC source. And it provides the voltage. How much it is? V0 sine omega t. Alternating voltage. And this voltage is given to the pure resistor, has a resistance capital R. So whenever this alternating source is connected to this resistor, the current will be set in the circuit. How much it is? Let it be taken I. Now the question is the current is constant? No. If the voltage supplied to the resistor is constant, the current will be constant. There we are seeing in the case of current electricity or DC sources. But here, how the voltage is changing? Let us see. At t is equal to 0, the voltage is how much? 0. At t is equal to t by 4, it is maximum, and t by 2 again 0. 3t by 4, negative maximum. And reversing the polarities in that sense we can take. And again t is equal to t, the voltage is 0. Accordingly, the current also changes in the circuit. Now, here we are interested to find the expression for the current. How it is been changing with respect to the voltage. Is it in same phase or out of phase or making any other some angle? We need to do all such things after getting the expression for the current. Let us start. Now, we have got the voltage value. Instantaneous voltage is how much? V0 sine omega t. Let it be taken. So the voltage across the resistor, how much we are applying, instantly you will get the same potential drop across the resistor R. How much? The voltage across the resistor R is equal to the same V0 into sine omega t. This is the first equation. And with this voltage, we can write how much current is passing through this resistor at that time. We can call it as instantaneous current through the resistor. How much it is? I is equal to V divided by R. And what is V? V is the instantaneous voltage. We have got this one. And write down V is equal to V0 sine omega t divided by capital R. And we can write current I is equal to V0 divided by R separately into sine omega t. So what is V0 by R? Voltage divided by resistance, you will get the current. What kind of voltage it is? Peak value of the voltage. There we are talking about this point. This is the peak value. So when you divide the peak voltage with the resistance, you will get the peak current. So there you can write it as I0 into sine omega t. This is the instantaneous current for the given time accordingly with the voltage. And let it be taken as equation 2. So once you compare the two equations 1 and 2, the voltage with the current, we come to know that the function remains the same, sine omega t, here also sine omega t. So how the phase changes? There is no phase difference between these two terms. In that sense, when the voltage is 0, at the same time you will get the current is also 0. When the voltage is maximum, you will get at the same time you will get the maximum current, but the value will be different. Because when you compare these two, I can write I0 is equal to V0 divided by R. So let us see these two expressions. So certainly the magnitude of the peak value of the current is less than the peak value of the voltage. But they will be in same phase. At the same time t by 4, you will get the peak value of the voltage and you will get the peak value of the current. Like this it changes. You can see. So in this manner it is going. So this comes as the peak value of the current. After that, the voltage comes as 0 at t is equal to t by 2, there the current also comes as 0 at t is equal to t by 2. So both comes instantly 0 at the time half of the cycle. And again, the maximum current you will get at the peak voltage is maximum at this point. You will get the maximum peak of current. And again, when the voltage is 0, the current comes as how much? 0. So this curve represents the instantaneous current and this curve represents the instantaneous voltage. By looking at this graph, we come to know that the phase difference between the voltage and the current comes as how much? 0. There is no phase difference and the graph is going in such a way. When AC is passing through the pure resistor, the phase difference between the voltage and the current is 0. And you will get the power factor cos 0 is equal to 1. Then we need to find how much is the power which is dissipated across the resistor. The one we can say is it has instantaneous power and the second is the average power, let us say. So before that, let us draw the phasor diagram for this circuit. What is phasor diagram? We are expressing the voltage and the current with vector notation. This you can take it as x-axis, here is the y-axis. And as there is no phase difference, we can represent the voltage along the x-axis and the current is also along the x-axis. There you can see the voltage which is representing the vector has a bigger magnitude as compared to the magnitude of the current, both instantaneously as well as their peak values. We have seen their instantaneous values how much V is equal to V naught into sine omega t, and we got current I is equal to V naught by R is nothing but I naught into again sine omega t. And there is no phase difference between these two. What is V naught by R? It is the peak value of current. You can write I naught is equal to V naught divided by R. Now, instantaneous power, which is equal to instantaneous voltage into instantaneous current, V into I. That is equal to, there you can write directly. So V naught sine omega t and instantaneous current is I naught into sine omega t. There you can write V naught I naught sine omega t into sine omega t, you will get sine square omega t. This comes as a instantaneous value when AC is connected to the pure resistor. And what about the average power? That is very important compared to this power. How much it is? The average power, we have got the expression for the complete cycle, which is equal to Vrms into Irms into cos phi, where cos phi is called as the power factor. For this case, we have got phase difference is how much? 0, and cos 0 value is 1. You will get this value comes as how much? 1, because phi is equal to 0, cos 0 is equal to 1. And that is equal to, we know Vrms, we can write it as V naught divided by root 2, and Irms is again I naught divided by root 2, which is equal to V naught I naught divided by 2. This comes as the average power for this case. Now tell me, is the opposition here, the resistor offers opposition to the current? Will this resistance will affect with respect to the frequency of the AC source? No, because the opposition is directly depending on the properties of the given material, the kind of wire we are choosing. It is independent of the frequency of the source. When you plot the graph between the resistance of the given element with the frequency of the AC source, as it is independent, you will get the graph parallel to x-axis. It has got the value how much? It has got its own value, that this length represents that value which does not changes as AC source. AC signal is passing through the resistor. and this point is also important to us. So that's about when the AC current is passing through the pure resistor. We have got the expressions, and we are seeing the phasor diagram for this circuit, and also how the resistance changes with the frequency of the AC source. When the AC source is supplied to a pure capacitor, you can see here the source has the voltage V0 sin omega t is applied to a capacitor has the capacitance C. C is the capacitance of the capacitor. It is the basic property of the capacitor. It can hold the charges on their plates. There you can see the plates 1 and 2. These are conducting plates which are separated by a certain distance. When these two plates are connected to the AC source, there you can see initially we have got a positive polarity, which means from this side if you are seeing, it is connected to the plate 1. The plate 1 is initially neutral. So when you connect higher potential to the plate 1, the electrons will move from lower potential to higher potential. Because it is a neutral, electrons are moving in this direction. There you can see the dot represents the electrons which are moving away from the plate. And the conventional current will be moving in opposite direction to the flow of electrons. You can see on the wire, the current is moving towards the plate 1. And as this plate 1 is leaving the electrons, it has got the net charge is positive. And this plate will get the positive charge, net positive charge. Similarly, when the second plate is connected to the negative terminal, because we are talking about the positive pulse, this side is higher potential compared to this side. Now this is a lower potential. Now electrons will move from lower potential to higher potential. You can see the electrons are moving towards the plate 2 in this way. The electrons are moving towards the plate 2. As electrons are moving in this direction, you will get the conventional current is moving in the opposite direction to the flow of electrons. There you can see in the entire circuit, the current is moving in a clockwise direction. And take care that the current passing in between these two plates is 0. Here, no current is passing through it. And as we got the electrons motion there from plate 1 to this side of the alternating source, and on the other side the electrons are moving towards the plate 2, we have got the current in the circuit. That current is called as conventional current. Okay, now we got the current, and how the current changes accordingly, the current will accordingly changes with the applied voltage. Is there any phase difference? Let us see once. At any instant of time, the charge which is stored on the plates, how much charge on the plate 1? It is a positive charge, let it be taken plus q at a given instant of time. The same negative charge will be stored on the plate 2, because the motion of the electrons, the leaving of electrons, how many electrons are leaving from the plate 1? The same number of electrons reaches to the plate 2 in the same time, according to conservation of charge. So let Q be the instantaneous charge. The Q be the instantaneous charge which is stored on the capacitor plates. At that instant, we have got a relation between charge, potential and the capacitance. What we can write? Q is equal to C into V, where V is the instantaneous voltage, C is the capacitance of a capacitor which is fixed, and Q depending purely on the applied voltage. How it is changing, accordingly the charge also changes. And now if you differentiate this equation, because it is a variable, you will get the current. So I is equal to how much? dq by dt, which is equal to C into d by dt of applied voltage, which is changing with the time. We need to take this expression. So V0 into sine omega t. Is it okay? Now, C into derivative of this term. V0 is constant, you can write outside. Derivative of sine theta, you will get cos theta. But theta, we have got omega t, we need to differentiate omega t also. So you will get how much? Cos omega t into differentiation of omega t is omega, you can write outside. Here you can write omega. And that is equal to, so you can rewrite this term in such a way, V0 divided by 1 divided by omega into C. And 1 by omega C, you will get the initial equation C V0 into omega. We are rearranging it this way. Into cos omega t. And this is equal to V0 divided by, I can changing this term 1 by omega C as a new constant which is called as the reactance of the capacitor. Let it be taken as XC, where XC is called as the reactance of the capacitor. How much opposition which is being offered to the flow of current by the capacitor is called as capacitive reactance, denoted by XC into cos omega t. This is the second equation and this is the first equation. So when you look at these two equations, here the function is sine, here is cos, and for to compare these two, both the functions should be either in the sine or in cos. So we need to change this one like this. So how I'm changing? So I is equal to V0 divided by XC into sine. We can write it as sine 90 plus theta. Second quadrant, sine is positive. You will get cos. So sine 90 plus theta or omega t plus pi by 2. And this you take it as the equation number 2 instead of this one. Now compare the equations 1 and 2. Because here we got same function sine and sine, we can compare easily. Omega t here is the phase. Here for the current the phase is omega t plus pi by 2, which means comparing these two, when AC is connected to pure capacitor, the current is leading the voltage by how much? 90 degree. The phase difference between the current and the voltage is equal to 90 degree. We can write in this way. Phi 1 is the phase of voltage, how much? Omega t. Phi 2 is the phase of current, omega t plus pi by 2. And the phase difference between these two, so phi 2 minus phi 1, which is equal to omega t plus pi by 2 minus omega t cancelled, you will get the phase difference is pi by 2. So what I am taking initially, the phase of the current. So the current leads voltage, ILV, current leads voltage, how much? By 90 degrees or pi by 2 radians. So this is a very important result regarding this circuit. So whenever AC supply is connected to pure capacitor, the current leads the voltage by 90 degrees. There is a phase difference between the current and the voltage. Here we can see graphically. So how we can represent the pulse of the current along with the voltage. There you can see we have got the result, current is leading voltage by 90 degrees. So the voltage is started at this point where at t is equal to 0, the potential drop across the capacitor is how much? Instantly won't get directly the potential difference across the capacitor, it will take time. But by that time already t is equal to 0, we have got the electrons which are moving across the wires. With that you will get the current. So E is equal to 0, instantly you are getting the maximum current. So from here we need to start. The graph. So this is the peak value of the current. And then the current is gradually decreases. There the current becomes 0 where the voltage is maximum. Here voltage is maximum, here the current comes as 0. Now I am plotting the current graph. Now here voltage is 0, you will get the current is maximum at this point. There you can see the graph is going in this way. There you can take at this point. And again the voltage is maximum, you will the current is 0 at this point. Where the voltage is 0, you will get the current is maximum at this point. Now combine all these points like this. You will get the current graph. You can see at t is equal to 0, voltage is how much? 0. By that time the current is maximum. And t is equal to t by 4, the voltage is maximum, the current comes as 0. At t is equal to t by 2, voltage is 0, the current becomes as maximum. 3t by 4, the voltage is how much? Maximum, the current comes as 0. And t is equal to t, you will get the voltage is 0, the current is maximum. So by looking this graph, we come to know that the current leads the voltage by 90 how much? 90 degree. And comparing the expressions, the peak values, we can write. So we got how much? I is equal to I naught sine omega t plus pi by 2, where I naught is equal to V naught divided by x into c. We have got this result for the current. When we compare this equation with this one, so what we can write here, V naught by xc is equal to how much? I naught. Comparing the peak values. So I naught is equal to V naught divided by xc, where xc is equal to how much? 1 divided by omega into c, which is equal to omega V naught into omega into c. And look at these two terms there, I naught which is equal to V naught into omega c. They have got their values here in the product form, omega into v. Multiplying with this, you will get the V naught. And when you multiply these two, you will get the peak value of the current. So this is the relation between the current and the voltage with their peak values. How much is the power dissipated across the resistor? Again, we have got the two. One is instantaneous power and second is the average power. Let us see first the instantaneous power. So instantaneous power is equal to how much it is? V instantaneous value into current instantaneous value. How much V instantaneous? It is V naught into sine omega t. And I instantaneous, we got it as I is equal to I naught into sine omega t plus pi by 2. We have got the result. When you multiply these two, you will get V naught into I naught and sine omega t into what is sine 90 plus theta? It is second quadrant. You will get the positive and sine changes as cos. You will get cos omega t. Suppose I can rearrange into a single function. I can do it this way. So V naught I naught divided by 2 into 2 into sine omega t into cos omega t. And look at this term, 2 sine theta cos theta, we can write it as sine 2 theta, which is equal to, so V naught I naught divided by 2 into sine of 2 omega t. And here the frequency of the instantaneous power, there you can see omega is the angular frequency for the instantaneous voltage and instantaneous current. And when you take the instantaneous power, we have got the frequency how much? Double the frequency of the voltage and the current. And this point is important to us. The frequency of instantaneous power is twice the frequency of either the voltage or the current when AC is connected to the pure capacitor. This is the instantaneous value. Let us take the average power in this case. P average. How much the expression? Vrms into Irms into cos phi, where the phi is the phase difference between the voltage and current. How much we got? The result we got it as the current is leading the voltage by 90 degree, isn't it? For the pure capacitor. So the phase difference is equal to 90 degree. You will get cos 90 value how much? 0. When this term comes as 0, you will get the average power in the case of pure capacitor is equal to 0, average power. For the complete cycle across the capacitor, there is no power dissipation, and this comes as a very critical point for this concept. The average power dissipation across the capacitor is always how much? 0 for the pure capacitor. We have got the instantaneous power. We have seen earlier. Average power is how much? 0. And look at the phasor diagram here. The phasor diagram represents the voltage and the current, how the vectors are changing. Now, the current is leading. Suppose if I am taking the voltage along the x-axis, this is the voltage value, and the current is leading the voltage, the y-axis represents the expression for the current, and the current is leading an angle how much? 90 degree with respect to the voltage, and this represents the phase difference between the voltage and current is equal to 90, in that the current is leading the XC, which is equal to 1 divided by omega into C. What is capacitive reactance? It is the opposition offered by the capacitor to the flow of AC current. When we talk about resistor, the resistor offers opposition to the flow of current. Similarly, the capacitor has got a property to oppose the alternating current, and this is called as the reactance of the capacitance. And by looking at this expression, we can write 1 by omega is equal to 2 pi f. So 2 pi into f is the frequency of oscillations into capacitance. When we relate XC with frequency or XC with the capacitance, we come to know the relation is inversely proportional, and the graph you will get is a hyperbola like this. Either you can take XC on the y-axis, the frequency of oscillation along the x-axis. As the frequency increases, this capacitance, the reactance of the capacitance will decrease in this manner. And this graph represents what is the nature of the graph? It is called as hyperbola, rectangular hyperbola. And the same kind of graph you will get between XC with the capacitance also. When we increase the capacitance of the capacitor, whose reactance will decrease in the same manner. The shape is again the rectangular hyperbola. And suppose if we apply the DC source to this capacitor, for the DC source, as you know, angular frequency is equal to how much? 0. Omega is 0, F is also 0. Then XC comes as 1 divided by 0. Anything but 0 comes as infinity. This comes as infinity. So the capacitor offers infinite amount of resistance to the flow of AC current for the DC source, where the angular frequency is equal to 0. And for the AC source, as we got it, offers some resistance is called as reactance. And in this case, if you apply very high angular frequency, very high omega, and we maintain omega value is very high, there you will get XC is equal to 1 by, if omega is maximum and XC will become minimum, might be it is equal to 0. Now the capacitor is acting like a conducting wire, or we can say it is a high pass filter for the flow of AC current under this condition, where the angular frequency is maximum, XC is minimum, which is nearly equal to how much? 0. So with these two, so we can take the statement for the DC sources, the capacitor blocks the current. For the AC source, it offers some resistance, it allows some current. If suppose if the angular frequency is maximum, the capacitor does not offer any resistance, almost zero resistance to the flow of AC current. We can call it as a high pass filter, or the capacitor is acting like a conducting wire, a normal conducting wire. Here in this case for the DC, it is acting like a pure open circuit. When it is open, the current in the circuit comes as how much? Zero. So when the capacitor is connected to DC, it blocks the DC current. The capacitor is acting like an open circuit. When it is connected to AC, under the one condition, if the angular frequency is maximum, the capacitor is acting like a pure conducting wire. We can call it as it is being like a short circuit. Current is easily passing through the capacitor even if it is connected in the circuit.